Although bond-line structures are nice and they're a lot easier to use than Lewis structures, the problem is they tell an all or nothing story. Either something is a single bond or it's a double bond. It can't be somewhere in between. In actuality, bonds are more of a cloud of electron density, where the electrons are smeared across the different atoms in a molecule. The way that we talk about this in organic chemistry is in terms of resonance. Resonance structures show us all of the different opportunities to smear this electron density around. So let's take the acetate ion, for example, CH3CO2-. Let's draw that out. 2 carbons. There's one of our oxygens. There's our second one. We can add some lone pairs. Oxygen on the right has a formal negative charge, so it's only making one bond. Okay, the other resonance form you guys should recognize for this is where we draw a double bond on the bottom oxygen instead of the top. So what does this really look like? Let's draw some orbitals. These sp2 hybridized atoms, in particular the carbon and this oxygen, are going to be trigonal planar. But in the bottom example, the carbon and this bottom oxygen are trigonal planar. So let's draw it as a trigonal planar. We've got our methyl group coming off to the left, and then going backwards we have one of our oxygen atoms, and coming forwards we have the other oxygen atom. For a pi bond to be made, we have to have a p orbital here. We've got the negative charge down here, which is also going to be a p orbital, and in the back we're going to have a p orbital for the other part of the pi bond. In reality, the electron density found in this negative charge on this bottom oxygen is actually spread up here through resonance and up here. So instead of having a double bond only at this position, it's actually more of a double bond spread across all 3 of these atoms. And this is how we get a resonance hybrid. So how do we draw a resonance hybrid? We look at our 2 resonance structures and we combine them. So in each case, we've got a single bond to the carbon and the oxygens. Sometimes we have a double bond on the top oxygen, sometimes we have a double bond on the bottom oxygen. So what we're going to do is draw a dotted line across, saying that happens sometimes. That electron density is spread across all 3 of those atoms. Sometimes the bottom oxygen is negative, sometimes the top oxygen is negative. So they're going to have partial negative charges instead of full negative charges. The most significant resonance contributor is always going to minimize charge. One of the rules of organic chemistry, one of my rules, is atoms don't like charge. Basically, it gives them a higher energy. And in nature, anything tends towards a lower energy state. So if we can eliminate charge, we're going to be lower energy, and the atoms are going to be more stable. As a corollary to my rule that atoms don't like charge, some atoms like charge more than others. More electronegative atoms are going to be more stable with a negative charge. More electropositive atoms are going to be more stable with a positive charge. We're going to go through these rules as we talk about more resonance structures. But let's go back to the acetate and see how these rules apply. Okay, we have our 2 resonance forms. I'm not going to draw the lone pairs here. I'm starting to get a little bit lazy. And these 2 forms alternate. So now we ask ourselves, can we minimize charge? Which one of these minimizes charge better? Well, each of them has a single negative charge, so none of them are really any different. Is the negative charge on a more electronegative element? In both cases, yes, it's on an oxygen, which is relatively electronegative. We don't have any positive charges in this example. So both of these are equally weighted. These have the same general energy. The other thing we need to talk about in organic chemistry is how we transition between the 2. How does this form convert to this form? Well, let's draw in our lone pairs real quick. And on the right side, what this negative charge is doing is it's shifting from the bottom oxygen to the top oxygen. So what we're saying is we're taking this lone pair, and we're making a new pi bond. We're drawing a double-headed arrow from the negative charge to where the bond is forming. This carbon now has 5 bonds. Carbon can't have 5 bonds. So as we form this new bond with our double-headed arrow, one of these bonds, the pi bond, will break and deposit a lone pair of electrons on the top of the other oxygen atom. We can go backwards the other way too. Take this lone pair, collapse it down to make a new pi bond, break the old pi bond, that'll give us a lone pair. There are 5 circumstances where you should recognize resonance. This is not a list that you should memorize, but this is something that you should be familiar with, and as you get more practice, you'll recognize more. Okay, so the first example is when we have a lone pair adjacent to a pi bond. So this enol, for example. Let's redraw it with our lone pairs. Again, we're not really drawing the bond between the oxygen and the hydrogen, that's okay. Now, the most electron density is actually found in these lone pairs. What can happen is we can take the electron density from the lone pairs and make a new double bond. When that happens, we have to break a double bond and we'll put a lone pair on a new place. So what is that actually going to turn into? Well, we've got a double bond here that was newly formed between the oxygen and that carbon. Because oxygen is making an extra bond now, it will be positive. It's making 3 bonds. It's formal positive. This carbon down here now has a lone pair and a negative charge. Notice the net charge here is 0. This positive and this negative cancel out to 0. Just like the net charge in this molecule, or this resonance form, is 0. If we drew a resonance hybrid of this, we have single bonds, just as we did before, but now we have a double bond spread out across both of these, with a partial negative charge here and a partial positive charge here. So let's go back to the rules about which of these resonance forms is a major contributor. First thing is we need to minimize charge. Which of these 2 forms, 1 or 2, minimizes charge? Well, 1 doesn't have any charge, so that tells you right here that this is going to be the more stable resonance form. Atoms don't like charge. In example 2, we have 2 charges drawn with the arrows. Another idea is we're trying to put negative charges on the more electronegative elements. In this case, we've got a negative charge on carbon. That's not good. Carbon's relatively electropositive, and we have a positive charge on oxygen, which is an electronegative element. This is not a great example of a resonance form. Second circumstance, if we put a carbocation adjacent to a pi bond. Okay, so let's redraw this. Now, if we think about the pi bonds here, the p orbitals, we have a p orbital here making the double bond, and here. But, as we discussed previously, a carbocation is basically an unfilled p orbital. So what can happen? You can easily see that maybe the electron density that's normally spread over here can spread over here as well, so that we're minimizing this positive charge, trying to reduce charge. So let's draw the 2 resonance forms. If the electron density is drawn to that hole, the positive charge, we have a new resonance form where the double bond is formed over here. The carbon on the left lost electron density. It's going to be positive now. Okay, the net charge we started with was positive. We ended up with a positive net charge. Okay, we can go backwards just by drawing an arrow this way. If we want to draw a resonance hybrid, we have our single bonds. The electron density is spread across all 3 of those carbons, and each of them is partially positive. This is an example of why resonance occurs. What we're doing is we're minimizing charge. Okay, number 3, if we have a carbocation adjacent to a lone pair. Let's draw our structure here with a lone pair. Oxygen has 2 lone pairs. You could think that maybe the oxygen, because it has electron density, can donate some of it towards that hole, that empty p orbital. If that happens, we now have a double bond between the oxygen and the carbon. We now have a positive charge on the oxygen because it donated electron density to the carbon. It's making an extra bond. So, are we minimizing charge in this example? Yes, we're spreading the positive charge out between 2 elements. which one of these two resonance contributors is major, though, is going to be this one. Why? We put the positive charge on carbon rather than the electronegative oxygen. Sometimes you'll have a double bond. You can draw resonance forms for this as well. Oxygen, if we look at our dipole here, oxygen's electron withdrawing. You always want to follow dipoles when you're doing resonance forms. If oxygen is withdrawing electron density, you could say maybe it would pull apart one of the pi bonds so it has a lone pair. If this happens, what we've done is we've taken a bond away from the carbon, so it's now positive, and the oxygen now has an extra electron, so it'll be formally negative. Okay, which one of these is the major contributor? It's going to be this one. We're minimizing charge. But what we are doing is we're saying that this happens sometimes. And this helps explain our dipole, and it helps explain some of the reactivity of the carbonyl functional group. Last example is if you have alternating pi bonds in the case of benzene. We could draw benzene like this, or we could draw benzene like this, where the pi bonds are in different locations. We can draw arrows to represent how they move. If this bond shifts down here, this carbon has too many bonds, so this bond will shift here, giving this carbon too many bonds, so this bond will shift here. In the end, we end up with this structure here. The resonance hybrid is going to be an average of the two. It's not really favored for either one because there's no charge and we're not minimizing anything here. We're just delocalizing the electron density across all of these carbon atoms. A lot of times, because organic chemists are a little bit lazy, we're not going to draw a dotted line. You'll see benzene represented as our hexagon with a circle in the middle, saying the electrons are spread out across all of those carbon atoms.